So today I'm going to be talking about nanotechnology trends in the lubricant market and opportunities, issues, because nano is actually getting very popular in the past 10, 12, 15 years. And in many cases, it's this definition is abused quite a lot. So what is nanotechnology and how it's been used in many industries? So is definitely moving the industry in the right direction because the new material of the similar chemistry or same chemistry, but in different size and sometimes in different morphology as well. So we have evolution in many different markets, right? From automotive, communications, and right now with a leap in certain markets, we can't even think how people were communicating with old systems back only 80 or 90 years ago, or even 10 years ago. It was very different. So the world of nano is really, really big. Also, nano means very, very small, and you can find this nanotechnology in electronics, in cosmetics, and in some in footwear, in towels, in you name it. All different applications that have nano, and they naming it nano. Either they have nanomaterials in them or not. Nano just became a very popular buzzword, and that's a pros and cons in that. So there are also some products in a lubricant market claiming that they have nanotechnology in them and call it nano-lubricant. However, nano-lubricant to me, as a company that produces nanotechnology and nanomaterial in a commercial scale, so we are the only company in the world that makes tungsten disulfide in spherical shape, controlling both size and morphology on a commercial scale. We're not lab scale. We're full commercial with two manufacturing facilities supplying this material globally, worldwide. So for me, nano doesn't mean anything. Nano means just size. Something is very small. That's all it means to me, at least. So the added value for nanotechnology and nanomaterial, also everybody claiming the same points, that it improves the performance of the lubricants, can be added to many different fluids to cover greases, automotive oils, top-up additives, industrial oils, metalworking fluids, and coatings, adding such properties as anti-friction, anti-wear, extreme pressure, and cooling properties, as well as many, many others. But as I mentioned, nano is just a size. So you can measure anything in nano. So in this case, your ballpoint of the pen is also nano. It just has 1 million of nanometers, but it's really not a nano particle there. But nano, again, is just a size, so anything can be measured or transferred to the size. So the real question to ask when you're dealing with a nanotechnology in general is there are three main points. Of course, what is the size? But the other important points are what is the morphology of the material and what is the chemistry behind that. Those 2 points are equally or sometimes even more important than just size. So there are different type of solids and nanoparticles. Tungsten disulfide, or IF-WS2, is a new generation of tungsten disulfide, known in the industry as one of the most lubricant material existing for past 60, 70 years. It's a new generation of that material. They're spherical particles with a hollow core. Then regular molybdisulfide, it's a platelet type of particles. Graphene is also platelet type of particles. Diamond-like carbon is also small particles, but they're solid, there are no hollow core, they're near to spherical as well. So if we analyze different type of nanoparticles that exist there, and some of them presented in this table, you need to look at it in a different standpoint of view on metal bonding capacity, pressure, impact resistance, oxidation and thermal resistance, chemical reactivity, dispersion stability, and toxicity. So most of the material are either excellent in all of those points or medium in those points, depending on the media they actually added to and in what form they are. So also, they're all pretty good in metal bonding and pressure, impact resistance, oxidation. Chemical reactivity is medium, and dispersion is primarily is a function of formulation, how well you can disperse them in a large scale, of course. Everything what I'm talking about is not a lab scale, is actual commercial scale. So we're looking at everything from a commercial standpoint of view. And tungsten disulfide, if you see here, toxicity is medium, is because it depends on what state you're using them. If it's in a solid form where material can be airborne, it can be harmful for ice, of course. But in our case, we produce primarily dispersions of those materials in a various liquids. Thus, toxicity is not an issue because tungsten disulfide is non-toxic material. So what is IF-WS2 stands for? I is inorganic, F is fullerene-like, submicron or nanoparticle of tungsten disulfide. We cannot call them fullerenes because fullerenes is a terminology dedicated only for carbon material, but since we're also spherical or near to spherical shape, we also we call it fullerene-like. And as I mentioned, regular tungsten disulfide is known for many, many years as one of the best solid lubricant on Earth. We created a new generation of this material, controlling morphology, controlling the size, and controlling the dispersion of this very wonderful material in liquids. And those liquids could be oil, could be water, could be alcohols, and we're getting quite phenomenal results in all of those liquids. So if we compare similar type of chemistries like IF-WS2 comparing to molybdenum disulfide of a regular shape, a legacy structure, we can see several very important benefits. First of all, tungsten disulfide of spherical shape, our IF-WS2, has a near to spherical shape. And it has very good tribological performance, and what is very important, absorbs shock. And I'm gonna show you on the next slide, the video under high resolution transmission electron microscopy video, how these particles absorb the shock and all those mechanisms I'm gonna talk right now about. So because of the spherical nature and hollow core, under the shock and impact, this particle absorb it, and they have a very good elasticity. Unlike many other solids, which are regular crystal structure and doesn't have a hollow core, they transfer the shock to the metal surface and creating micro pitting and micro crack. It was shown many times in the past, probably 12 years, that tungsten disulfide spherical particles absorb the shock and reduce dramatically micro pitting and micro cracking by absorbing that shock, having this unique morphology with the hollow core. It has a wide range of applications because the particles are small and dispersion is much easier than a regular micron-sized particle of molybdenum disulfide or tungsten disulfide. Thus, applications are not limited only to grease, as with molybdenum disulfide, or primarily to grease. We also use them in metalworking fluids, in oil, industrial oils, automotive oils, coatings as well. The low treat rate, because the size is very small, and smaller the size is higher surface area, and the treat rate goes down. So we observe the treat rates from 0.05% up to 2%. Have excellent anti-wear and anti-friction properties, phenomenal extreme pressure protection, and that's when I'm going to show several slides on that. It's cost-effective and non-toxic, is eco-friendly, and is REACH registered. With molten disulfide, because of the structure of the platelet type of structure, they demonstrate moderate performance on tribology. Before IF-WS2 was known, for example, like 25 years ago, it was one of the best solid lubricant. Right now, we increase the standard. So they have no shock absorbing properties because they transfer the shock and they don't really protect from micropitting. They are used in a heavy load and low speed application primarily, and they really require very high treat rates. Usually lubricants and primarily greases, as I mentioned, they have between 3 to 8% of molten disulfide. So on this video, I'm going to show, you're going to see the different mechanisms. So you can see that under microscopy video, they start compressing the particle, and you can see that it's compressing and it has a quite a good elasticity. At some point, the layers of tungsten disulfide are getting exfoliated, and that's your friction reduction mechanism, the exfoliation of layer after layer. If you notice that particle moved to the right, it bounced back to near to its original shape. That's your shock absorbing properties. But the layers that right now you see on the screen is quite tacky, and it's your tungsten disulfide. It's very strong. So it's creates a protective film on the surface of the metal and create and reduce wear and increase wear resistivity of that layer on the metal. And this particle, again, ready for another cycle of exfoliation, because this particle has between 18 to 30 layers of tungsten disulfide. So it's getting consumed, but that's what you actually want, because you want to create more and more of these protective layers on in your system. So in this short video, you pretty much saw friction reduction, that's your exfoliation mechanism. You saw the shock absorbing or extreme pressure properties in one of this material by absorbing the shock by compressing and having high elasticity. And that is very important when we talk about extreme pressure, to talk about both dynamic and static extreme pressure. Because when we're measuring extreme pressure with the 4-ball, which is a typical test for extreme pressure, we pretty much running at a certain condition with a load applied slowly on the system, but we don't really observe impact resistivity of the system. So it is very important to know that these particles protect from regular extreme pressure or static load, as well as dynamic load like shock. So why being nano is not enough? First of all, you need to synthesize solid nanoparticles in powder form. Excellent. You got your material, you got your solids. They're showing you phenomenal results in some applications, primarily in lab scale. But then you need to make sure, as professor before me mentioned, that you're making very homogeneous and stable dispersion of it in the desired liquid. And it's extremely important. You need to control the size, you need to control the dispersant and surfactant that you use, and making very stable material. And then you need to make sure that when you're adding that to the final lubricant, you still maintain stability and performance, to make sure that your final lubricant is compatible and all the components are compatible with your nanoparticles. Because the final lubricant is a combination of many components, not just anti-wear, anti-friction, extreme pressure. It also have anti-corrosion additives, metal deactivators, biocides in some cases, antifoamers, and many other components. So you need to make sure that your nanoparticles and surfactants of your nanoparticles are stable and are in line with other components that are going into the lubricant. That is extremely important. What are the opportunities and risks here? So of course, we know we have the better performance. It's a long-lasting results, it's optimized production, it's lower overall cost of ownership. Very, very important points for any industrial applications because performance is not the only driver for end users. They're not ready to pay any price for performance. They're always the price for performance that they want to pay. So the risks there are high prices. Many nanoparticles are unstable in many fluids. Supply consistency also very important. So you may get phenomenal results, but when you're scaling it up, those results are not there anymore. The governmental regulation right now, you see, especially in Europe, they're more regulated, and they're all asking questions about toxicity, about long life cycle of the material, how to handle those materials, how to dispose of those, and so on, and environmental concern. So the drivers, of course, are there as well. So demands from OEM and end users are big, and they're quite challenging. That they need to reduce the cost of ownership, they need to reduce the downtime, they need to reduce the energy consumption, they need to improve the performance at the same time, increase equipment life. They need to make sure that whatever they use, it doesn't come as an expense for environment, and waste removal issues not going to be there. So they need to know that there are not going to be changes in operating environment, and this material is going to work in any environment as well, with a high load, low load, high speed, low speed, various temperature cycles, humidity, and so on. So it's quite challenging demands, and yet quite fascinating. So the important tribological benefits of lubricants are there. So when we're talking about anti-wear, anti-friction, extreme pressure, dynamic static load, micropitting prevention, all good. This doesn't mean much for end user in many cases. Those are general phenomenal terms for scientific fellows, but then that need to be translated to higher performance and increase equipment life and optimized efficiency. And that's then actually needs to translate it to savings. What that gonna translate to end user, because all they care about are saving, reduction of cost of ownership, reduction of downtime, reduction of energy consumption. That is our main drivers for them. So talking about anti-wear, anti-friction for the end users doesn't mean much. So if we compare molybdenum disulfide and IFWs2, the visual appearance is black because that's a natural material. They're different shape and different geometry. Extreme pressure for molybdenum disulfide is okay. It used to be outstanding. Right now the standards are different thanks to Nanotech Industrial Solutions. Right now, IFWs2 is a new standard for extreme pressure, anti-wear, and anti-friction properties. So talking about, again, about the mechanism, there are several of those. As I mentioned, yes, there's the effect of ball bearing, the rotation of the particles on a surface. However, the rotation on the surface of the spherical particle is a function of the surface roughness. So it's not going to rotate on any surface. So we believe, also there are probably hundreds of papers showing that IFWs2 particles do rotate. We believe there's not a predominant effect of the friction reduction of the IFWs2. The predominant effect is exfoliation of the layers, sliding effect. Due to submicron size, they can fill the asperities. If you can see on this picture over here, let me get the pointer. They can fill the irregularities on a surface and smooth the surface. So that's also going to affect friction reduction and anti-wear properties. And of course, as I mentioned already, the unique shape with the hollow core, that's your protection from extreme pressure and micro-pitting, which is extremely important for gear applications. So now I'm going to show the several slides on performance that been tested on Ducom Instruments. Thank you, Ducom, for running most of those tests for us and with us. This data that I'm going to be showing to you is just for general purpose. It was not very technical. My discussion wasn't very technical. However, there are a lot of technical slides here. So just to compare IFWs2 on a fundamental standpoint of view, in water versus 100% oil, just to have very broad picture on the comparative effect, how IFWs2 works and what it can give. So it's kind of mind-changing slide showing basically 100% of oil, SN150, which doesn't have any additive yet, it's just base oil, however, it's 100% of it, versus 99.8% of water and 0.2% of IFWs2. And on extreme pressure four ball, we already outperform. So basically 99.8% of water outperform 100% of oil on EP. Of course, with 1.5% of IFWs2 and 98.5% of water, there's no weld at all, okay? So this material doesn't weld. And we're talking about 98.5% of water. If we're gonna look on the lubricities, right now it's a different test, it's G99, it's a ball on disc, and we're comparing the commercially available water-based lubricant and friction on that. So it's quite good compared to water, of course, but it's a water-based lubricant, so it has some polymers in it, so it has some friction modifiers, water-based. So that's a friction over here. It's going up and then goes down due to formation of the tribofilm, due to polishing the track, because you can imagine the ball is rotating on a disc and the surface getting worked. So the friction may go reduce due to that as well. But then you can compare it to Candex, again, the same oil, Candex 150 as a group 2 oil. So friction is much better because it's oil. And 99.7% of particles and 0.3% of particles and 99.7% of water. So you can see that friction is even better than oil. So what are we talking here? Are we talking really that let's replace all the oil with water? No. Also, that's a very interesting discussion. Of course, you can add here viscosity modifiers and all the other different additives to make a finished product, but the potential of this is very big. Of course, you cannot use it in applications which are high in temperature because it's water and it's going to evaporate. But the concept is here. So IFWs2 provides very high performance from tribological standpoint of view, as well as from the cooling standpoint of view. And we did those tests as well by improving the cooling capacity of water by about 20%, which is very significant. So I'm gonna speed up here and show several slides that have been done at Ducom. So basically, we took emulsion, which is oil and water at 10%, and compared with a combination of reduced emulsion with IFWs2 particles and IFWs2 particles by itself. And we get really significant improvement, of course, in extreme pressure. So we get, this is 4-ball, but not ASTM standard 4-ball test, but DIN standard 4-ball test. So we got really good improvement in extreme pressure with just particles or particles with emulsion. But what is really interesting is the temperature increase. So it looks like with IFWs2 particles, the emulsion got very significant reduction in operating temperature, which is very important for many applications such as metalworking and many others, because the lower the temperature, the lower the degradation of the lubricating fluid, as well as the increase the life of the equipment and parts. I have several slides in greases as well here, and it's comparison of grease with IFWs2, with monodisulfide, and with PTFE. So we see that with IFWs2, we got increase of the weld loads from 160, which is regular lithium complex grease, to 800 kilogram force. With monodisulfide, we went from 3 to 10%. We got increase in EP. However, it was not as good as with much lower concentration of FWs2. But with PTFE, with 3% and 5%, we didn't see any EP improvement. So it stayed at the same level. However, it improved some anti-wear properties. And it's very interesting plot of IFWs2 versus molybdenum disulfide. Molybdenum disulfide, because of the size and shape, is known as a very good anti-wear reduction solids, but primarily for low speed applications. But 4-ball is not a low speed application, it's a high speed application. Thus, you can see increase in wear. So it's very important in what application you're applying your nanoparticles or micron particles or just any particles. It doesn't work it's not a panacea, it doesn't work for any application. So you need to be very careful applying the material to the right application. That's why you see increase in monodisulfide. If we would increase the load and reduce the speed, you probably see decrease in wear as well. So as a summary, I would like to say that lubricant additives based on nanoparticles have higher performance in general. Also, you need to really pay attention to size, shape, treat rate, and not all nano-sized particles are the same. Very different mechanism in many cases, and it works very differently. So you need to apply this material to the right application and consider many points that I mentioned before, stability, of course, and compatibility with the other components in the lubricant. So again, important to remember that shape, morphology, chemistry of particles are as important as the particles. This technology been developed in 1992 by Professor Rashef Tana in Weizmann Institute of Technology in Israel. He was on I believe he was on a short list of Nobel Prize for that in 1992. So in 2002, the company been established to commercialize this technology and scale it up. So currently is 2020. Yes, we have 2 plants here in US and in Israel. We're making tens of tons of this material in a solid form, and we're making dispersions of those material in various liquids. So we're full commercial. We're supplying it worldwide. So it's not, what I'm showing here is definitely not something that it's not something that is very exciting, however, not available. It is available on a large scale.
George, do you have a comment on the shelf life? That the question from right.
The shelf life, there are several points with the shelf life. If you're talking about stability in a various form, we have stability. We see stability up to 2 years right now. We do recommend in various applications to keep the shelf life between 6 months and 2 years, depending on what dispersion that is. If we're talking about water-based dispersion, if we're talking about oil-based dispersion or alcohol-based dispersion, it's a function not only of the particles, but it's a function of the media that is going into. And it's not function only of stability as well. It's a function of oxidation, it's a function of any other. So shelf life is is a more broader topic rather than stability only. It combines the other very important point of shelf life, which is again oxidation, changing in parameters. It could look stable, but performance can go down. That's also something to really keep an eye for.
One question on NIS. I had a long chat with the professor when I met him in Israel. Can you comment on overall cost benefit analysis? I'm a commercial lubricant formulator and marketer, and IFS2, I mean, the data looks so attractive. In fact, believe you me that in my own team, in my own lab, at my R&D center, we have the most elaborate facilities for lubricant development. And we very seriously looked at WS2 and IF also. But most of the tribology data does not translate into the real engine performance. And even if it translates, the cost which was quoted by several commercial entities is not giving me a favorable net cost benefit analysis, because I'm a commercial marketer, so I need to first look at the cost is also one of the imperatives and deliverables for me. And I'm willing to even consider the total cost of ownership. I know that nanomaterials are costly. With that consideration also, I approached that if the overall total cost of ownership proves to be net positive, I'm willing to adapt that in at least some of my top-notch product line of my lubricants. But what is your take on net cost benefit analysis? I'm not really going into the nitty-gritty of improvement in anti-wear or extreme pressure, whether PTFE is good or WS2 is good. I myself can argue for or against of one or the other nanoparticles. But nano additives per se, what is the net cost benefit analysis? Did they reach that stage?
We believe it did. Again, we for quite a long time, we already working with many world leaders in lubricating manufacturers. So the cost benefit analysis depends on the formulation you're putting, is number one. We making dispersions from 5% concentration of IFWs to 50% IFWs to concentration in water and in oil. So they're low concentration, high concentration. We making different with different surfactants, with different type of fluid. I mean, we have about 12 to 14 product in our line. The price, you saw the approximately the concentration of IFWs2 in a finished lubricant, which could be from 0.05 to 2%. Again, depending on the application, on the type of lubricant you're trying to produce. So the price there is for our concentrates. I can give you just a ballpark, but we can talk about that separately in discussion. They're way below $100 per kg. So and then actually you can multiply both percentage on that, and you can see that it's very cost beneficial. We're not talking about hundreds of dollars as primarily nanoparticles going. And you can see that the treat rates are from 0.05 to 2%. In some cases can be a little bit more, but again, I can't really right now discuss any application, but I'm talking about many applications. Right. So that's actually bulk part. So cost analysis could be also need to take into consideration removing certain anti-wear, anti-friction, and EP agents and replacing them with IFWs2, right? Because we're talking about the competition for the surface, and you don't really want to oversaturate your lubricant with the other components. So that's also could be cost beneficial, not add on the top of what is there, but to balance it, make sure it's very well balanced formula, and tribological performance is supplied by IFWs2 primarily. That also another beneficial, cost beneficial point to optimize both performance and cost of the lubricant. So there are many points there to discuss, but overall we see with our customers that we are cost beneficial. Otherwise, we would not have those customers.
Thank you.